Hey guys, welcome back to Mr. Esterberg's classroom. It's me, Izzy Schamberger, and make sure if you like this video to give it a thumbs up and subscribe, and make sure to click that bell notification so you can know whenever we post a new video.
Looking at use substitution for these integrals, and one option is to actually take x squared plus 1 to the fourth, multiply it all out, times 2x, and integrate everything individually. Yuck. Instead, we're going to try this. We're going to let u, the variable u, be equal to the innermost function x squared plus 1. And also in doing that, we're then going to take the derivative of both sides of this blue equation. So we would have du dx equal to 2x. Take the derivative of both sides with respect to x, we get this. And mathematically, this isn't really the proper thing to say, but you can think about it this way. Multiply both sides by dx. So we're going to write down du is equal to 2x dx. So what is significant about this? Well, once we put all this stuff together, we're going to get a simpler integral to figure out. So it's the integral of, I see in the original problem there is a 2x dx that's highlighted in yellow, and based off of the work that we've done, 2x dx is equal to du. So inside of our integral here, we're going to put du, because that's what that yellow part is equal to in the original problem. And also, there's this blue part. It says x squared plus 1 to the fourth, but since u is equal to x squared plus 1, we're going to rewrite this as u to the fourth. So now this integral is going to be much simpler for us to solve. Not necessarily simple, but definitely simpler. We are taking the integral of u to the fourth du. The variables are the same, and that is significant. So when we're using the power rule to integrate, the u to the fourth becomes u to the fifth. We divide it by 5, because that's what the new exponent is, plus then c, our constant of integration, because it is an indefinite integral. Now, the original problem did not have any u in it. It had only terms of x's, so we're going to substitute back in the fact that x squared plus 1 is equal to u. So our final integral then is going to be x squared plus 1 to the fifth over 5 plus that constant, and there's our answer. How do we know that's correct? Well, if you were to take the derivative of this, it should get you back to the original problem. In the next example, we have this integral. Inside of the square root, we have x cubed plus 1, so we are going to let u be equal to that x cubed plus 1, which means du over dx is equal to 3x squared, but eventually we're going to move that dx to the other side so it looks like this. And this is shaping up pretty nicely already. We'll have the integral of, well, this part of the problem is u, the square root of u, so that's u to the 1/2. And then the 3x squared dx, I see from this work down here that that's equal to du. We're integrating u to the 1/2 with respect to u, which is nice, those variables are the same, which is going to make this u to the 3/2 divided by 3/2, or easier understood as multiplied times 2/3, plus our constant. Going back and rewriting the final answer, it is 2/3. Instead of u to the 3/2, the original problem had x in it, so it's x cubed plus 1 to the 3/2 plus c. How do I know this is correct? Is if I took the derivative of this, it gives us back to the original problem. Example C, we want to integrate this one, so we're dealing with trig functions this time. I could let u be equal to secant squared of x, but then when I took the derivative of that, it would get kind of confusing and it wouldn't match up with what we have here. However, if we let u be equal to the tangent x plus 3, and then take the derivative of this, the derivative of tangent is secant squared of x, and we're going to have that dx after it, which is matching up very nicely with our original problem. So then bringing all of this together, we have the integral of the secant squared of dx, that is the du part of this one. And then tangent x plus 3 is the u portion. And instead of being like a typical trig function where we know the derivative of this is that, or integral of cosine is whatever, we have a power rule now. We have the integral of u du. So when we integrate it, it's going to be u squared over 2 plus c. And then if we go back and substitute in, u is equal to the tangent of x plus 3. So that's squared over 2 plus c, our constant of integration. So there is our integral. How do I know this is correct? Well, if I took the derivative of this should get us back to the original problem. This next step, it says we need to make a minor adjustment in each integral, and we'll see what that is here in a moment. As I look at this one, inside of the function, the most complicated thing is this x squared plus 1. So we are going to let u be equal to x squared plus 1. Take the derivative of both sides, and with simplifying, we get du equals 2x dx, which isn't exactly what we have on the inside. We only have 1x dx. So to make this work, we need to multiply the inside by 2, so now that looks like a 2x dx. But since we multiplied the inside by 2, we also then have to divide by 2, or multiply by 1/2 to balance that out. So what I have up here in blue is 1/2 times 2, that's 1, it's gone. It didn't impact the answer, it just made it possible to do, but it is equivalent. Now bringing this together, we have 1/2 integral of, and this 2x dx, we can plug du in for that. And for the x squared plus 1 to the 6th, well, since we let u be equal to that, that would be u to the 6th on the inside. Now we'll integrate. U to the 6th becomes u to the 7th, divided by 7. We have the 1/2 out in front because it was already there, plus our constant. And we do have to write a little bit more for this one because the original problem didn't have a u in terms of it. So the u becomes x squared plus 1 to the 7th over 7 times 1/2, and you can leave it like this, or you can multiply the 1 over 2 times the 7 in the denominator, just call it a 14 down there, and you can have your answer like that as well. In this problem, we're going to let u be equal to 2x plus 1, so du equals 2 dx. Inside the integral, it just has 1 dx. We need it to be a 2 dx, so we're going to multiply by 2, and then also by 1/2 to balance it out. Bringing this together, we have 1/2 integral of u to the 1/2 du, because the square root means the 1/2 power. And when we actually integrate that, that's going to be u to the 3/2 divided by 3/2, or really times 2/3, plus our constant. This 1/2 has to carry down as well. I can cross off those 2's. So it's going to be u to the 3/2 over 3, that is 2x plus 1 to the 3/2 over 3, plus our constant. So the more confusing part is what's underneath this square root sign, the 4x cubed minus 5. So as you're thinking, what should I let u be equal to? I'm going to let u be equal to that 4x cubed minus 5. So then du is equal to 12x squared dx. And we're running into a similar problem that we had in some of those other ones. Go ahead and draw our little arrow. We have the integral of this 4x cubed minus 5 is to the 1/2, but it's in the denominator, so that whole part of it becomes u to the negative 1/2. In other words, this, because of our u substitution, is going to be equal to that. However, this 7x squared dx is not the same thing as 12x squared dx. We don't want 7, we want 12. So what do we do with the 7 to turn it into a 12? Well, we multiply it by 12/7. 12 divided by 7 times 7, or 12/7 times 7 is 12. But because we multiplied the inside by 12/7, we're going to multiply the outside by 7/12. And now, this whole part of it that I have highlighted in blue, cross off those 7's, that 12x squared dx, we can call that du. Now it's like all the other problems, we just have this fraction of 7/12 out front, not quite as nice as some of the ones we've had before. So in integrating, we have the 7/12 u to the negative 1/2. We integrate it by power rule. In other words, we raise it by 1, which makes it become u to the positive 1/2, divided by 1/2, which really means multiply by 2. That's our constant. And as far as how much you simplify this, it's up to you. We do need to make sure we plug the 4x cubed minus 5 back in for this u. So it's 4x cubed minus 5 to the 1/2. I could say times 2 times 7/12, or if you want to simplify it, 7 times 2 is 14. 14 over 12 would be 7/6 plus our constant, and that looks a little bit better, but again, you didn't have to do it that way. And this one we're going to let u be equal to 2x, which means du is equal to 2dx times 2 times 1/2. So bringing this all together, we have 1/2 integral of the sine of u du. The integral of sine is negative cosine, so it's negative cosine of u plus c times this 1/2 out front. And then to bring everything back together, it's negative 1/2 cosine of 2x plus our constant. Here's the work for example 3b. If you would like to, you can pause the video, work through it, see if you get the same answer. But we're going to move on to example 4 on the next page. Next example, we have sine squared 3x times cosine of 3x dx. We're supposed to integrate this, and it's not really clear what we're going to let u be equal to. If you tried to let u be equal to 3x, then du would be equal to 3dx, and it's not going to work because we don't have everything in there that we need. In fact, what we're going to do this time, since this is the more confusing of them, we're going to let u be equal to the sine of 3x, and not even squared, just the sine of 3x. Because if we were then to take the derivative of this, du is equal to the cosine of 3x times 3 dx, and I can see how this is going to start working itself out once we substitute things in. So first of all, that yellow part, since u is equal to the sine of 3x, then sine squared of 3x is going to be substituted in here as u squared. So now those are equal, and it's in terms of u. This blue part isn't quite the same as that blue part yet. Now here's when we've done these kind of problems before. We just need a 3dx at the end, so times 3 times 1/3. So we're going to put a 1/3 right there. And now all of this blue is the same as that blue, which means it is du. And now we can integrate it. We're going to integrate it with the power rule again. It is a trig problem that's going to be integrated with the power rule. So u squared becomes u to the 3rd over 3. And that 1/3 is already out front, and then plus our constant of integration. To finish it off, we have to plug what u is equal to. So it's the sine of 3x cubed, or you could put the cube between the sine and 3x. I just like it this way better. And then 1/3 times this over 3. You could leave it like 1/3 times that over 3, or combine them to make it 9, plus our constant. Here's our example 5. We're supposed to integrate this, which is a binomial times a binomial with e to the x's in them, and it looks just horrible. Remember that derivative of e to the x is e to the x, the integral of e to the x is e to the x. These have e to the 2x plus another x times all that. It is in the realm of u substitution. That's why it's in here. What are we going to do with this one? Well, I'm looking at these two. The first one is a bit more complex than the second one because it's adding x rather than just adding 1. I'm going to try to let u be equal to e to the 2x plus x. That's this first part. Take the derivative. The derivative of the first part, the derivative of e to the 2x is 2 e to the 2x. The derivative of x is 1. All of that dx. And already I can see this is working out very nicely. This is what u is equal to. This whole part is what du is equal to. So all of this then comes out to the integral of u du. The yellow part is the u, the blue part is the du. What was an e problem is now a power rule. The integral of u is u squared over 2 plus some constant. And then we're going to make our substitution back. Instead of u, we're going to call it e to the 2x plus x squared over 2 plus our constant, and there's our answer. We could square this out, but there's no reason to do that. Leave this as your answer, and that's it.